Hello. In this video, we want to take a look at boosted forests, specifically stochastic gradient boosting, AdaBoost, and extreme gradient boosting. All right, so the approach here is rather interesting. What we're going to do, we're going to build a weak model, and then we're going to look at the errors, and then we're going to build a tree to fix the errors. Then we're going to look at the current errors, build another tree to fix those errors. Then we're going to build another tree to fix the remaining errors and keep on doing this over and over and over. So something that's critical about this is that we're going to be using very short trees to build our model. And so this is whenever you see boosting, boosting is this correct the errors approach to modeling. And we achieve this by having ensemble of multiple weak models to achieve this. Overall, we can improve our accuracy, but be warned, since I'm building models that adjust the previous errors, if I go too deep, if I have too complicated of models, I can overfit horribly in this situation. So we need to make sure that we put some guardrails up to protect ourselves from overfitting. So typically, we use decision trees for this, but potentially any model structure could be used. It has to be what we call weak learners, models that just don't individually don't have much predictive power because we don't want to overfit. And iteratively, we build trees to correct the mistakes of the predecessors. And boosting converts weak learners into a combination of one strong predictor. And this is extraordinarily effective. I've used this all the time at work. One downside to this is that I can't look at individual trees to really draw an inference. So if I was doing random forest, each individual tree is doing the best that it can by itself to model what's going on. While with stochastic gradient boosting, extreme gradient boosting, the tree that I look at is dependent on the previous performance of all other trees. And so individual trees don't really give me as much information as an individual tree would from random forest. All right, so let's go ahead and start working through an example. So boosting works to sequentially build models where we correct the errors of the previous models. And so this is kind of like, give me a piece of information. All right, then go to the next person. Okay, can you improve on that person's answer? Go to the next person. Can you improve on the previous answer? And keep on trying to get better and better until we nail it as a group. And gradient boosting is all about optimizing a loss function. Instead of aggregating the outputs of many models, like in bagging, such as random forest, gradient boosting focuses on the residuals, the difference between the observed and the predicted values. These residuals are used as targets for the next model. So this is very interesting that our target variable is not the target variable. Our target variable is the error on the target variable. Overall, predictions become a weighted sum of all the individual model predictions. All right, so let's take a look at some more specifics. All right, so let's say that I've got my observations and I've got my model predictions. Well, then my residual is just the difference between them. And our loss function, so here I'm using mean squared error, but we could use a different loss function such as mean absolute error. Well, I'm going to take the squared residual, add it up, take the average. And I could also use, if I was doing a classification project, there's other loss functions that could be used. But our goal is to minimize our loss function. Now we're going to be fitting our trees to the residuals. So in each iteration, instead of fitting the tree to the original target, we fit the tree to the residuals from the previous model. This means that each tree is trying to correct the mistakes of its predecessors. And we're going to do a weighted sum of predictions. And so the prediction comes from all trees combined together get a single prediction. And so here we're going to have a learning rate parameter, which will be a small positive value that is going to be used to determine how they're combined. All right, so let's go ahead and actually run through an example. So here I'm going to use that house prices data set from Kaggle once again. Previously, I decided that these predictor variables are reasonable to go with. And this is a Kaggle data set. The original data set has a train and test data. And I put them together, when I did my data prep, I put them together into one big data set. And the test set, I don't know the actual target variable. So what I'm going to do is I'm going to get rid of the ones where I don't know the target variable. And then I'm going to split my, what Kaggle calls a training data set into training and tests. And that's what I'm doing on this line here. Now I'm going to go through and build a stochastic gradient boosting model. All right, so there's some randomness going on, so I'm going to go ahead and set the seed. We have a continuous target variable, so I'm going to use a Gaussian distribution. Here I'm building the model on the training set, and I'm restricting the data that's being passed in to only my predictor variables and the target variable. So here, this is the target variable. This is my vector of my predictor variables. And so then this is nice. I can just use our formula notation. And we have to indicate how many trees we have. I chose to do 150. We have to choose what our interaction depth is going to be. I believe the default is 6 on this, which is, to me, kind of high. Shrinkage, the smaller shrinkage generally will give us a better fitting model, but I'm going to have more computation time for smaller shrinkage. And then, here is another parameter that we need to worry about. All right, so I've built my model, and we got some output going on here. There are 150 iterations, 150 trees. We had 25 predictors, of which 25 had non-zero influence. All right, so that's saying that all 25 of my predictor variables were used at some point in the model. If I was to see that, let's say 20 had non-zero influence, I would want to remove those 5 that had zero influence. That way, when I go back, when you do a real project, you end up going back and forth, back to previous states, and you really don't want anything to slow you down when you come back to it, because invariably you're gonna have to move back and work on things. All right, so now the GBM dot performance is a short for performance. Gives us a plot to see what our iterations look like. And so here I can see the squared error loss coming down, and it gives an estimate of where was the best number of iterations. So here I would consider, if this was a real project, going back and changing my number of trees to 50. Here is using out of bag change in squared error loss. So what's happening here is that not every row of data is being used. When we say stochastic, there's a randomness to this. And that stochastic aspect includes randomly selecting which rows of data to be included in the model. And so here, some of the rows are excluded from each individual tree. So when we build an individual tree, so a subset of the rows of data are selected to be used to build the tree. Some are excluded. And this is a bootstrap, by the way. And so the ones that are excluded give me like a holdout data set to check to see accuracy. And so this gives me my out of bag statistics by using that holdout set from the bootstrap. All right, so here we have number of observations, equivalent number of parameters, and residual standard error. All right, so some things that are important for us to, the super important parameters to worry about is going to be number of trees, the shrinkage or the learning rate, and the interaction depth or max depth. All right, and so and these are the same. They have different terms in scikit-learn and than in R, but it's the same concept either way. Shrinkage is learning rate. Number of trees is like maybe number of rounds, number of trees, depending on which package you're looking at. And max depth and interaction depth are what we're looking at for preventing the tree from getting too deep. All right, so let's go ahead and do this again, but this time, let's do it on that mushroom data set that I got from Kaggle. So once again, this is a Kaggle data set. We're classifying, is a mushroom going to be poisonous or edible? In this situation, 1 means it's edible, 1 means I can eat it, 0 means it's poisonous, I don't want to eat it. And we're going to be using the Bernoulli distribution. Here's my interaction depth, my shrinkage, and the minimum observations in node has to be 10. All right, and we had 5 predictors, and all 5 had non-zero influence. Okay, that's good. So now let's go ahead and take a look at the curve to see how many trees it looks like we would want to use. All right, so here, we can see a little bit less than 100 was optimal by this measurement. And so, I probably would go back and trim it down to just 10 trees, to just 100 trees. Here's using out of the bag. And, we see, like, yeah, I think 100 probably would have been good enough instead of 150. So here's the equivalent number of parameters is 12. That's interesting. And here's the residuals of our standard error. Now to get the predicted values, I just have to use the predict function, and we need a type of response because we want to see the actual value that we're trying to predict. And so here, this is basically saying poisonous or probability of poisonous, or sorry, probability of being edible is the model value. Now the calibration plots, what these do is that here's the predicted value. Here is that modeled likelihood of being edible. Here is the actual observed value of 0 or 1, and we can see how things average out. And so here, things aren't as strong as I would like. We can see that there's a spike coming up. If you remember the original data set off of this from a previous video, all of the predictor variables are 0s and 1s. So this peakedness is definitely coming up, or not peaked, but this high and this low are definitely coming from those 0s and 1s hard discrete values. And so I might want to go through and do feature selection on this model. Now here is doing on the test set. Well, on the test set, it looks better. I feel more comfortable about the curve here. We can see that we have a wide range, in the same region that we had that dip. All right, so there, we would definitely, I would definitely be going back to try and figure out why is it this way. All right, so let's talk about our parameters a little bit more. So we have our number of trees. We have our tree depth. It's called max depth when you do stochastic gradient boosting with scikit-learn. We have our learning rate, which is called shrinkage in the R package. The minimum number of observations for a split. We have our subsampling rate and that bootstrapping. And then we have our loss function, which will depend on what type of target variable we have. Now, it's important not to overfit. So if I was to go in and increase the maximum depth I could get and go with a really low shrinkage rate and then drop down the minimum observations for a split, I'll end up getting very, very deep trees. And trees by themselves can overfit. But remember, we're correcting residuals. And so it's like if I make a bad choice on the overfitting stuff, I can go off the rails horribly so. Decision trees by themselves without pruning, individual regular decision trees can overfit. Here, because of this correct previous errors aspect, there's more possibility for it. So we want to make sure that each of the individual trees underfit on each and every step. And I've covered this a bunch of times in other videos that overfitting reduces generalization. So like I can't go away from training set. We lose really just like the full range of our data if I overfit. Also, the overfit models take longer to compute. So I'm sitting there waiting for longer. And it just gets harder to interpret the overfit model. So protect yourself from it. Now, best practices, start simple. Start with shallow trees. If you don't know what to do, if you're unsure, go with shallower trees on this. Use cross-validation to get your best hyperparameters and stop early. It's okay to have fewer trees. It's okay to have shallow trees. Some of the algorithms that allow us to do regularization. That's a great idea. And also afterwards, go through your feature importance, trim out the junk that you don't need, and that will improve your model's actual performance when you get to your scoring data. So variable importance, there's a couple different ways to measurement. We have frequency based. So this is just a count of the number of times that a predictor variable is used. There's how much it reduces the impurity going on, so such as the Gini impurity or the entropy for classification. The one that I've seen the most for regression is just reduction in variance. Also, sometimes will be called ANOVA in some packages. And then we have permutation importance, where if we randomly shuffle a column, we check to see how much did the accuracy drop. And that if it dropped a lot, that's an indication that variable is very important. It can be very computationally intensive, though. All right, so by understanding our variable importance and double checking it and making sure that only important variables are in the model, will improve our interpretability of the model by trimming it down. And also by going through my variable importance, trimming out things I don't need, I'm doing feature selection, I'm going to improve the model. Now, something that's important is that when I might need to actually include predictor variables that I don't want in my model. So and this has happened at work. I've gone through my project, I've gone through my feature selection, I've built my model, and a stakeholder says, hey, what about variable this? Or my boss says, hey, what about this variable? And so some people just will have this prior belief that a certain variable is super important. Now that information may have been equivalently captured by other predictor variables, but they want to see it explicitly, even if they're not even going to look at it. My most recent example of this is my boss wants something to be be kept in the model, but she's not even going to get double check it. She's not even going to look at it, but she wants it in there. I'm an employee, I'm going to put it in there. Well, before then, I had trimmed out enough predictor variables. I had made sure that my model wasn't overfitting by a decent margin, that putting in a predictor variable that I really didn't want didn't negatively impact my model significantly. So I just put it in, double check to make sure it wasn't overfitting, and I ran with it. Also, down the road, the more predictor variables you have, the more prone to problems down the road can happen. So let's say your company stops measuring a certain value. They stop recording something when they take in a new client. Well, if you go grab that value and it's no longer there, you're going to get an error. You're going to have problems with your model. And so by having fewer variables in there, by only having the important ones in your model, you're going to be protected from having problems. Also, one that's very important for my work is that variable importance. I do a bar chart and I label the percentage of importance and I stack them, most important to the least, and I go to them. I say, hey, this is what I'm seeing. Does this make sense? Does this look like reasonable to you? Every time they've said yes, they'll say, huh, I'm surprised that that one is so low. But when something's really low, we have to consider that other predictor variables are also involved that are kind of muting it out, maybe beating it to the split. All right, so here this is typical of a variable importance plot that I would use at work. I would put more work into this one. I did this fast for the video, but you see I've got bar plots for the importance. So what I would do at work, I would actually have each one explicitly labeled dot 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 horizontally to read, and I would go ahead and put like the percentage importance on there, and so we could talk about what's in there. Is there anything that should be inserted? Is there anything that should be removed? And so here we can see the relative influence. And so if I was doing this for work, I would actually go through, remove this one, rebuild the model, then remove this and keep going. I like to have at least 1% for all of my predictor variables, just my personal preference. But I definitely would go through and trim out these small guys. Now here's for the mushrooms. So here we can see for the mushrooms, odor is by far the most important. It's dominating all of these. And in the decision tree video that I did previously, we saw that very clearly. So odor, then population, then spore print color, then stalk root, then bruises. And it's a summary function that gives us this output. Now, something that will happen if I have correlated features in there, and that could be like multicollinearity in a higher dimensional sense. What can happen is, especially, so imagine I've got 3 predictor variables that are nearly perfectly correlated. Then it's basically random on which one's going to get picked for a split. So when this like combination is the best split possible, it's random which of these 3 is going to get picked. And so what will happen if I have highly correlated predictor variables, my variable importance is going to look a lot lower for these 3 than it should. So you can think of it as these 3 would have 1/3 of the variable importance that they should have if I had only 1. And so how do I like to address this issue? When I go through and do feature selection using a model, I remove 1 at a time, trimming it out, get the least important one out, least important, so that of the 3, eventually I'm going to get to the one that had the lowest feature importance, remove that. Now these 2 are going to jump up in the list and be higher. And so when I go to the next variable to eliminate, I'm not going to hit these 2 more than likely because they've risen in importance. Now we can detect interactions with random forest, which is very nice. And so this a good feature of this model structure is that I can check to see, should I even consider interactions? So let's say that I have to do a linear regression model, but I don't know which interactions to include or exclude. Well, it works out that stochastic gradient boosting will actually give me like a score on interaction terms so that I don't have to manually check it. I could do statistical computing and run through the code, do a big for loop, and do it for me. And now when I look at the feature importance, remember that it's relative to each other. Notice that this adds up to 100. Notice that this adds up to 100. And so, when I look at these, if I look at 2 different models, it's always within the model that's being built. So I can't compare relative importance here to relative importance here unless I consider it in my head it's a percentage of what's going on. It's not the actual, like, it's not like a measurement of accuracy improvement or degrading. All right, so now to detect the interactions with boosted forest, something that is really nice for us is that we can go through and check the interaction ourselves. And so it's the interact.gbm function will go through and find interactions for me. Here I'm just randomly building something to check it for us. But here we can check we use the code, use the function to check the interactions between there. And so you'll see here, like it looks like here. Now this was Yeah. So yeah, I'm using the mushroom one. And so it looks like the strongest interaction is between the fourth and the fifth. So that would be stalk root and bruises. Now, something that is kind of a pain though is that, oh no, that's not an issue. But this gives me a tool. I can do a for loop like this to find which interactions I would consider if I was doing linear regression. And so this way I don't, like, I would know just not even bother with 1 and 4. All right, so there are some other different models. There are tons and tons of versions of boosted forest. The classic one is AdaBoost. Then I would say the most common one is stochastic gradient boosting. And then in Kaggle competition, extreme gradient boosting is very, very common for winning. So AdaBoost, which is adaptive boosting. So initially, all instances are assigned equal weights. After each round, the weights of misclassification are are increased, making them more likely to be correctly classified in the next round. The final prediction is a weighted majority for classifications or a weighted sum for regressions of the weak learners. Now, for stochastic gradient boosting, we use a fraction of the training data. Remember, we're doing that bootstrap. This induces some randomness and helps with preventing overfitting. And so this is where the stochastic name comes in. And we have our shrinkage to slow down the learning process to help protect us from overfitting. So this ensures that trees correct the mistakes of the previous trees in a gradual manner instead of overshooting it. And now stochastic gradient boosting, we need a differentiable loss function for this, by the way. Now, extreme gradient boosting is super popular in Kaggle. And so in a Kaggle competition, your goal is to have the most accurate model on the scoring set. So your goal really is to overfit on the scoring set. I don't like extreme gradient boosting for actual real life applications. It's excellent for like an accuracy competition, but an accuracy competition, you just need to be right one time. You need to be good one time. The goal is to overfit on the scoring. So I don't like that for the purpose of putting my name onto something for a long-term model. I think you would be better off going with like stochastic gradient boosting, random forest, like backing off of that extreme fit of your score data set. So extreme gradient boosting has some nice features. First of all, it's got regularization to help protect you from overfitting. It can handle missing data well. It can actually find the best imputations for splits. It does parallel and distributed computing very easy for you, so that sets it up. Now, something that's interesting is that it'll actually like go too deep and then prune, and that's part of the power of this one is that it will go deeper than it should be, trim it to get you a better individual tree. And we can also use customizable loss functions, which may be helpful if I'm in a more exotic situation. So of these three, AdaBoost focuses on reweighting instances and is often paired with simple models like decision tree stumps. Stochastic gradient boosting induces a concept of gradient boosting and random observation selection. Extreme gradient boosting is a very feature-rich gradient boosting, and it's fast and it gives good performance overall. Now here's an example of just using AdaBoost. So we would use the AdaBag, adaptive. So there's adaptive and there's bagging in this package. So it's the AdaBag package. Here we're using boosting. We also use the bagging function if we want to do something like random forest. And we can see how to fit the model. So here we can plot to help us get diagnostics. Here we can see like what's going on with our errors with each iteration. Here I'm doing it on the test set. I'm checking the test set. And so we can see it's a little bit, not quite as good, but still pretty good. For stochastic gradient boosting, look at the previous example. And then for string gradient boosting, we're going to use the XGBoost package. For trees, we want GB tree to be used. Now, something that's important is that we need to be entering matrices into here to be able to work with this. So, just that's a stumbling point. Make sure that you're passing a matrix, not a data frame for this. And in general, we can choose different objective and evaluation metrics, but they should be, like connected to each other. So mean squared error and root mean squared error, it makes sense to use them together. Now, why is extreme gradient boosting used in Kaggle competition? Well, frankly, because it wins a lot. That's why. It's got high performance. It's very flexible. It can handle a wide range of problems. It handles missing values well, so I don't have to mess with that. It does regularization and tree pruning. I like the tree pruning a lot. It does parallel processing. So if it's a big data set, I can get it done faster. It does cross-validation and does fine. I mean, it has just a lot of features. It's super important, super powerful. All right, well, that is boosted forest for supervised learning. That's all I got for you. Life is short. Do math.